Hey everyone, welcome back to this op-amp video series. In this video, I'll talk about loading effects and how to deal with them. Have you ever seen the lights in your house dim when your AC turns on? Why does that happen? Well, there's no such thing as a perfect voltage source. In this case, that means it's going to have some internal resistance. Ideally, its internal resistance or impedance should be 0, but usually it's not. When your load draws a lot of current, for example, your AC turning on, there will be a bigger voltage drop across the source resistance, causing the voltage seen at the load to be reduced. And this reduced voltage makes your lights dim. Loading effects are a very common issue that need to be dealt with in high and low voltage applications. Let's take a look at an example to help illustrate what loading effects are and how to mitigate them. Let's say we have a perfect voltage source that outputs a 1 volt DC signal to this 100 ohm load. This isn't a trick question. You can clearly see that the entirety of the voltage from the source will drop across the load. What happens when the voltage source has some internal impedance, let's say 1 ohm? So this voltage seen at the load would be 100 divided by 100 plus 1 times 1, which is 0.99 volts. Essentially the same as the original 1 volt DC signal with just a 10 millivolt drop or just 1% error. What if the internal impedance is now 100 ohms? Plug it into the equation and we get 100 divided by 100 plus 100 times 1, which is 0.5 volts. Now the voltage that the load sees, which we were thinking would be 1 volt, is now just 0.5 volts, half of what we want it to be. So how do we fix this? Usually what we'll do is use a buffer or voltage follower. Voltage followers have huge input impedance and incredibly low output impedance. Let's draw out an example. Let's say we have a DC voltage source of 2 volts with an output impedance of 100 ohms. Our load resistance is still 100 ohms, so let's put a buffer in between the source and the load. The MCP6006 has a differential input impedance of 10 to the 13 ohms. And with the feedback, it's even more, so that's just massive. Let's just say it's 10 to the 13 for this calculation. From the datasheet, the closed loop output impedance plot shows the impedance for a gain of 1, like our buffer, and we see that at 1 kilohertz, it's about 1 ohm. If we were to continue that slope down to DC, we can see that the output impedance will be negligibly small. Let's just say 1 milliohm. Now let's do some calculations. At this point here, let's call it A, we have 10 to the 13 divided by 100 plus 10 to the 13 times 2. I mean, it's 2 volts. And at our output voltage here, we have 100 divided by 1 milli plus 100 times A, where A is 2 volts. So again, basically 2 volts with negligible error. Using a voltage follower is a very common approach to addressing loading effects. If you want to learn more about voltage followers, check out the other videos in this op-amp series. Thanks for watching.